I will speak about interconnected systems. Everybody knows that ISS framework is very useful when you study stability of interconnected systems. But in some sense, this presentation will be a kind of anti-ISS presentation, or to be more precise, it will be a kind of anti-small gain presentation, because we will derive conditions which are in some sense alternative or a bit better than small gain conditions. This is a joint work with Ivan Atamas, who is a PhD student, and Vitaly Slinko, who is his postdoc, both in my research group at the University of Würzburg. So let's begin. If it works, yeah, it works. Yeah, subsystems that are interconnected, given by some ordinary or partial differential equations, for example, maybe have some external inputs, but today without external inputs. And it is known that studying such interconnections in view of stability, typically people assume that each subsystem satisfies some stability property like ISS, passivity, or more general being a vector Lyapunov function exists, or for each subsystem Lyapunov functions exist. So each subsystem is needed to be stable in some sense, and then eventually by means of some additional conditions like small gain conditions, one concludes that this feedback connection is again stable. Many results also for more than two interconnected systems exist. Them assume that each subsystem is stable in some sense. What can we do if at least one subsystem is not stable? Then actually not too many works exist studying also this possibility. I mention a few. Basically, this is more or less all works that I know. 2015, there were subsystems, discrete time systems, where in fact the small gain framework was extended to the case where some subsystems can be not stable. And so these are very interesting results, but they are finite dimensional first, and second, discrete time, and I have no idea how, if it can be extended to continuous time systems. Moreover, dimension plays a big role in this work, in both these works. And as far as I remember, in case of a large dimension, the results become a bit hard in use. A more recent result by these three authors, the first one and the last one are co-authors also this presentation. They developed also an approach to study interconnected systems, periodic systems, finite dimensional ones, so that many of them can be unstable. And again, I asked them, they have no idea how or if it can be extended to infinite dimensional case or to more general classes of systems. And the last result that I'd like to mention, it is just very recently published a couple of weeks ago. Interconnection of an ordinary differential equation with a one-dimensional parabolic was studied in this work, and also in this case, the ODE was not necessarily presumed to be stable. But also in this work, we have a very particular class of systems, and at the moment, we do not know how this can be extended to larger classes. So the motivation is now to find at least some other approaches, or possibly more general approaches. In fact, what I show you here will be also limited to a special class of systems, but at the end I will say several possibilities how we expect that our approach can be extended to other classes. Our setting is as follows. Here is our interconnected system. The first one is one-dimensional, which is of course a big limitation in this work. And the second one is infinite dimensional. It is with a Hilbert space. And given in this abstract form as abstract differential equation, where D can be also unbounded. So here we assume that D is closed, densely defined, and dissipative in the sense that this inequality holds for some non-negative gamma. As well, we assume that there is a positive number in the resonant set of D. Okay, these properties in particular imply that D generates a C0 contracting semigroup. And our aim is to study stability of this interconnection. Let me remark that if A is negative, we immediately see that the first subsystem is stable, or if you like, ISS. And the small gain condition boils down to this small gain condition has a very big advantage. It is usually easy to check, and then you get global exponential stability for this interconnection by means of small gain condition. So in the negative A is a good case where you can apply something like ISS theory and small gain condition, etc. But now our aim is to study the case A can be non-positive. So what can we do? Small gain condition does not apply, and we need to develop some different approach. Here I just recall the definition, what is global exponential stability, which tells us, so the system is globally exponentially stable. By definition, if solution to this system is bounded by the norm of the initial state, not times e to the minus alpha t, alpha is positive, and you have this exponential decay. Okay, this is just to recall the definition, and now the main result. The main result is as follows. Again, here is our interconnected system. I introduced this notation H and L here just for simplicity or for compact presentation of stability conditions. And the stability conditions are here. First, we need that D, so that D minus 1 exists. The second inequality can sometimes, so it resembles a little bit the small gain condition. And in fact, in very particular cases, it even coincides with it. But here, A is not necessarily negative. The last three conditions can be interpreted as restriction applied on B, C, and D. As you see, B and C are parameters responsible for interconnection. D is dissipative, so the second system is good and the first subsystem can be bad. In particular, if A is positive, it is unstable. But these three inequalities restrict or relate the dissipativity properties, action properties with this C and B. If all these inequalities are satisfied, then the whole system is globally exponentially stable. And this is our main result here. And let me remark that the last inequality can be replaced with a more rough condition, which is easier to check, but it is more rough. The advantage is that you do not need to take care about so another remark is that, as you see, we have more inequalities. It looks more difficult than small gain approach. But this is one price that we need to pay in case we would like to cover more general class of systems, so that here the first subsystem is allowed to be not stable. So A can be this main result. I give you some applications and illustrating examples demonstrating how this approach can be used in particular cases. And the proof of the, first I speak about the proof, and then we speak about applications. Yeah, the proof is split basically in 6 lemmas, and then at the end I will use these lemmas to conclude the proof of the main result. If we write down this, where A is defined by the right-hand side of our system, then the first lemma is as follows: assuming that 0 is in the resolvent of D and that A does not coincide with this constant, then there exists inverse of A, and it can be calculated by this relatively simple formula. This formula is actually a direct extension of the inversion of block matrices. Sometimes this inversion formula is called Frobenius formula, and this is its infinite dimensional counterpart. And the proof is just by direct calculation of a product A with A minus 1 to demonstrate that you will get identity. The second lemma is as follows. Again, we have our system. This is the same right-hand side as previously. And here, the assumptions, let me go back for a minute. The assumptions that we apply here, that D is closed, densely defined, dissipative, and with a positive number contained in the resolvent set, these assumptions are throughout the whole work. And yeah, in this case, second lemma tells us that the system is well posed. The sketch of the proof is as follows: because D is
closed. Can I interrupt for a moment?
Yes, please ask.
For you, I'm a bit puzzled about your inversion of A there. I mean, so you want to say that 0 is in the resolvent set of A, then essentially?
Yes, yeah. So
okay.
0 is in the resolvent set of D.
So H inverse is identity. I mean, that can only be true in one direction, right? In the other direction, it's the identity on the domain. That's something else.
Mm-hmm.
Okay, just checking. Thanks.
Yeah, so anyway, as I said, 0 is in resolvent of D, and this additional condition allows you to get inverse on this, and it is defined then on the whole space, so it is linear bounded, the inverse, and yeah, the proof is just routine calculation. Yeah, for the well-posedness, yeah, because D is closed, densely defined, dissipative, we have also first the closeness of A, and then A1, which is this shifted A, also dissipative for at least large omega. Then we prove that for sufficiently large lambdas, or for all lambda 0 large enough, it holds that lambda 0 is in the resolvent of A1. Then we use Lummer-Phillips theorem. Then A1 by this theorem is generating a contracting, and also A generates a semi-group, and yeah, this basically proves that the system is well posed. Yeah, if you have other questions, then please interrupt me and ask. So next lemma is number 3. Related for this lemma, I need a notion of cone. We say that as subset, a non-empty subset K, which is convex and closed, is called cone in this Hilbert space if this scaling property is true. That is, for any x in K, the multiple of x with positive non-negative lambda is also in K. This intersection is just 0, and also we use the adjoint cone, which is defined by, by this inequality. Okay. Yeah. So having this cone, we state the following lemma. Let A be some generator of a C0 semigroup, not necessarily as in our system, but just some general generator of a C0 semigroup. And so that this implication is satisfied for all couples Y of K star and X of K, non-zero. Non-zeros, if these two vectors are perpendicular, then this scalar product is non-negative. If this is satisfied for some solid cone K, which also satisfies this density condition, then it follows that the flow generated by our differential equation is positive with respect to this cone. Positive means that no matter at which point you start in the cone K, the flow, and the sketch of the proof is as follows. Here we use that K is solid. Solid means that it has non-empty interior, so it contains some non-zero vector eta in it. Then we, instead of this equation, this differential equation, we perturb it slightly with some small positive epsilon and consider this equation. We prove that for initial states in this intersection, the intersection for all times. And then again, using the density, these density properties of K, we take the limit when epsilon goes to 0 and prove that also this flow for any initial condition in the K, the solution remains also in the K. And this finishes the proof by this limit argument. Next lemma. In the next lemma, I need a special code. In the previous, let me go back. Here, A is some general generator of a C0 semigroup, and K is this rather general cone defined here. And on the next slide, K is Dashkovskiy cone defined by this inequality, which is already by this definition always solid, self-adjoint, and has many other properties, which I don't discuss here. And if we specify our A to exactly what we have in our interconnected system, then by means of this condition, it follows that our system is positive in the sense that, yeah, if you start in the cone K, then the solution remains in this cone for all times. The proof, we know that Y and X are perpendicular, so the scalar product is 0 for X, Y in K. Now K and K star is the same. Then we check that there exists a positive lambda, so that these equalities are satisfied. For these equalities, I have prepared a picture. So first note that perpendicular in this specific case of this inequality, if this scalar product is 0, then the Y and X lie on the boundary of the cone. I have a picture. Yeah, so this is vector Y, the big one, and this short dashed vector is vector X. Because they are perpendicular, they need to be on the boundary of the Minkowski cone. So here K is again this Minkowski cone. And in fact, so X0 is real number, Y0 is real number, and then X is this vector and Y is this vector. And by geometric, relatively simple considerations, one can indeed prove that these equalities are satisfied. The next step is, again, if we have two orthogonal vectors, and then use the condition that we have in our lemma by some direct routine calculations, one can verify that this inequality is true. And now we can use the previous lemma. In the previous lemma, this inequality implies this positivity property. Let me go back for a second. Yeah, so here, if we have this implication, then the solutions, or then our system is positive, meaning that this inclusion is satisfied for all times. This is exactly what we get here at the end, and this proves this lemma number 4. Now the next lemma is for the case of bounded operators. If we instead of A, consider this operator B, and the only difference is that this T is now bounded. So here T is bounded. Now, if these two inequalities are satisfied, this one and this one, then this operator is strongly continuous in the sense that application of B to any point in K, maybe on the boundary, brings you to the internal point of K. Well, here, as I said, B is bounded, and I wanted to mention something, but the proof is just routine calculations where you need to use different properties of Minkowski cone, and so I will not give all details of this lemma. Okay, here K is again Minkowski cone. This is important. It's not general, but exactly Minkowski cone. And now the last lemma is as follows. This lemma is a kind of comparison principle. Let us see. We have this positivity property for all times, and if we take any x in the cone, also in the domain of A, and let theta be such that this inequality is true. Now, if this is true, then for the solution to our differential equation, the same inequality is true with respect to the cone. And also in this lemma, the cone K is Minkowski cone as above. So this is a special case of Minkowski cone. And the comparison is as follows. If AX bounded by theta x, then solution satisfies the same inequality with respect to cone for all times. The idea of the proof is as follows. We first prove that this lemma is true for bounded A. For this reason also we needed this previous lemma for bounded operators. Now if then we check that for large enough lambdas, this for the resolvent of A, we have this inclusion, this invariance property. Resolvent is then defined for large lambda by this formula. And then for A, which in case of unbounded A, can be approximated by Yosida approximations. Yosida approximations are bounded operators, and we have already proved this in the first state for bounded operators that our lemma is true. And now we check that for Yosida approximation, this inclusion holds, this inequality holds, and using the first step, because A lambda is bounded, we conclude that this inequality is true. And the last step is to take limit for lambda going to infinity, and using that the difference between these two, the norm of this difference goes to 0, and this allows us to conclude that this inequality holds already for A, not only for A lambda. So these are 6 lemmas that are used in the proof, and now the proof becomes short of the main result. First, we have well-posedness by lemma 2. Then this inequality used in lemma 4 was also used in the statement of the main result. This inequality implies the positivity property. Then, with help of lemmas number 2 and number 5, we can check that there exists such vector k non-zero in the cone, so that if we define W by this expression, then it will be in the interior of K and also in the domain of A, so that this inequality is satisfied. Now we use comparison principle in lemma 6, so that this inequality implies this inequality for all times. And then it is just direct routine calculation where we use many properties of Minkowski cone. Minkowski cone is part of being solid, is also normal cone, non-flat cone. Then after some calculations, we can really prove this exponential stability for our original system. Okay, and let me recall that A in all these situations can be not necessarily negative, but can be positive or zero. Okay, now we arrive to examples or applications. And the first application is to the connection of an ordinary differential equation with this partial differential equation where D is a differential operator defined by this formula, which is assumed to be strictly elliptic. Defined on this domain, and here we have initial and boundary conditions. So this is our initial conditions. These are directly boundary conditions. And for this operator D, we can check that we assume that 0 belongs to the resonant of D, and we assume that it is dissipative, meaning that for some positive constant, we have this inequality. Yeah, by these properties, again, by Lummer-Phillips theorem, we know that D generates a contracting C0 semigroup in L2. And then for the inverse, to write down the inverse, we need the green functions. And this is actually the price to pay for, well, in our approach. If we like to get more refined results than small gain results, then at this stage we need to calculate the green function. But note that in some cases, or in many cases, calculation of green function can be easier task than calculation of spectrum, or it can be easier than finding a Lyapunov function for the whole system. And in our examples, we will see that it really works. So we have examples where this G is given explicitly. So this is illustration how, it's not illustration yet. Now we apply our theorem to this interconnected system. And after some elementary but difficult calculations using this heavy notation, which you do not need to remember, just see that this H, theta, J1, J2, J3, etc. are all defined in terms of our system, parameters of our system, and we need a green function, the green function of our system. And now our theorem, our main result, guarantees global exponential stability if 4 inequalities hold. This was the same as exactly in theorem in the main result. First, then second, third, and fourth inequalities. If all these are satisfied, then our system is exponentially stable. Well, here this plus is truncation by 0, and lambda max is the maximal eigenvalue of J3. And as a small remark, the last inequality, this one, can be replaced by a more exact, more rough inequality, but easier to check inequality by this one. So this is illustration how it can be applied in this kind of interconnections. And next, we would like to compare our results with a small gain condition. To make it more visible, I introduce so this was our original system, and this term and this term are interconnection terms. And I multiply here by beta and here by beta. So here we have beta and beta. And now another important property is the dissipativity properties, and mu scales how much dissipativity we have. So now we have two parameters, beta and mu. Beta is a kind of interconnection gain. Mu is responsible for how much dissipativity we have. In order to apply, we can apply our main result, and in order to write the stability conditions, we need, again, this, unfortunately, some heavy notation, but again, you do not need to remember all of this. Just look at these 4 inequalities, 1, 2, 3, 4. These 4 inequalities written in terms of parameters of our system guarantee that the whole system is global asymptotically stable. And in particular, A can be positive here, but now we especially interested in case of negative A, because in case of negative A, small gain condition can be applied. Okay, and here I recall the small gain condition, which can be easily derived in this situation. And our main result splits into three possible situations. A is negative and this color product is negative, or A is negative and this color product is positive, and the third one is just where A is positive. Then we have only this one possibility in order to get stability. Now let's try to compare. Let us think what happens for large mu. Large mu means you have very strong dissipativity of second equation. If mu, so just fix all parameters and send mu to infinity or make it large, then we see that restriction on beta is of the order mu squared to the power 1/2, so it is of order mu. And if we compare with our result restricts beta by minimum of these three numbers. And here we have mu square, and here mu to the power 1. And for large mu, minimum will be here. And if we compare this and this, they are very close to each other. At least they are of the same order. And in many cases, they even coincide, which shows that our result in this situation is very close or coincides with the small gain condition. But again, if A is negative and this scalar product is positive, then the situation is different. Our result provides restriction on beta. This is the interconnection gain, basically, in this form, where we have mu square, and for large mu, this bound becomes very large. So for very large mu, we have almost, much less restriction than here in the small gain condition. In the small gain condition, the restriction is of the order mu, and here it is of the order mu square. And of course, for large mu, our result is much better than the small gain result. And in the very last case, A positive, the small gain condition cannot be applied at all. So in this case, you cannot conclude about stability by means of small gain condition, but our result provides you with this two-sided condition applied on beta. And again, this is better than in small gain framework, where we can conclude nothing in this case. Okay, now a particular example, interconnection of an ODE with an ensemble. Ensemble is parameterized by theta. Theta is between 0 and 1. So here alpha, beta, BC, etc. are described here. We have initial conditions, and this operator D, now looking at here the right-hand side, is given by this formula. So in this case, D is bounded operator, and it is dissipative with constant gamma defined by this expression. So we can apply our main result to this simple situation, simple because D is bounded. And after some elementary but long calculations, we arrive to 4 inequalities, 1, 2, 3, and 4. If they are satisfied, then the system is globally exponentially stable. Again, A is not necessarily negative. Now, in the very particular case, if we choose D, B, C, etc., all functions as special functions, some specific functions, then the dissipativity constant is close to 4. If we choose A to be negative, then we can apply our result and get this restriction on beta, or we can apply small gain condition and then we get this restriction on beta. And as you see, our restriction is definitely better than this restriction. So we have again advantage over small gain. And in case of positive A, the small gain condition does not work, it cannot be applied, but our result provides these bounds if beta satisfies these two inequalities. Then we conclude that the whole system is globally exponentially stable, which again demonstrates an advantage of our approach. And the last example is interconnection of an ODE with parabolic PDE. Note that we have here variable coefficients in the second equation. The state space is this one, H2 intersected with H01. Initial condition, boundary condition of the Dirichlet type. And yeah, so these are parameters of the system. Now, so D0 is denoted by minimum of D of the whole interval. Here this D is unbounded, defined on this set. Of course, it is densely defined on L2. It is well, one can verify that it is also dissipative after some calculations. So our main result can be applied, and again, after some calculations, these four inequalities guarantee that our interconnection system of an ODE with this parabolic PDE is indeed exponentially stable. Now, if we take, now I can show you the green function in this case, so it can be written explicitly, and this allows to verify all these conditions. So, in fact, if you think about calculation of spectrum for this D, I think explicitly it with variable coefficient with variable D, it probably cannot be resolved at all. But here we can write down explicitly this green function and check these conditions. So finally, a particular situation, if we choose L equal to 1, B, C, etc. by these functions, then for negative A, we can compare with small gain. For negative A chosen minus 0.2, we get this bound. Small gain condition gives you this bound. So again, our approach, at least in this case, provides better conditions. And in case of positive A, the small gain condition again cannot be applied, but we have this two-sided restriction on beta and arrive to global exponential stability. Again, this demonstrates the advantage of our approach. So now we come to conclusions. Yeah, we have developed some new sufficient stability conditions for interconnection of two systems where we do not require that at least one subsystem is not required to be stable. It can be unstable. And we have demonstrated advantages over the well-known small gain approach by means of examples. And also we have illustrated by these examples how our approach works. And now about possible extensions. Of course, it is a big restriction that our first subsystem is one-dimensional. But we expect that maybe instead of cones, if we use wedges, maybe we can extend this result to a situation where the first subsystem is, say, n-dimensional. But other possible extensions are to use different types of cone, like non-convex cones, or we can refuse Hilbert space and consider cones in LP. Another idea just recently proposed by Vitaly, the co-author of this work, is to use theory of spaces with the indefinite metric. Now, our approach was only for linear systems, but for nonlinear systems in the literature, the monotonicity property that we have used here in our approach, there exist conditions of monotonicity for the flow with respect to this cone. This is a standard cone, Rn+, and we hope that these known conditions can be also extended to Minkowski cone, and also not only finite dimensional, but maybe infinite dimensional case. So these are already several ideas which we hope to develop in the future in order to get more flexible, to extend our approach to more general classes of systems, including nonlinear ones. Thank you for your attention. That's all. And now I'm open for questions.